Hello, we're going to look at another method that you can use to show the complexity of a divide and conquer algorithm. This one is called Substitution Method, which actually is just induction. In the previous lecture, you saw how we can do this using the recursion tree method. And you might be wondering, why do we have to know about another method? Well, because sometimes you may not be able to draw the tree nicely. So what we did in the last lecture was quite exact actually, because we draw the tree and we look at how many operations you're doing in every single node. So you're actually counting the number of operations very precisely. But with this technique, it's not as strong, I would say, because you are using induction. But it's good when we don't know what the tree looks like, or it's hard to work out the tree, or maybe we want to prove a weaker bound. As in, something can be big O n squared, but you can't see it. We can't see it from the tree. Can you at least show that it's big O of n cubed, maybe? So that's one possibility. But yeah, this is probably going to be more useful if you intend to do more research, more computational theory. So I kind of look at this lecture as a way to make you better at doing proof by induction, like showing you what can be done by induction. Before we talked about using induction to show the correctness of an algorithm, and now we're using induction to show the complexity of an algorithm. And you also get to see common mistakes that we do when we prove something by induction. And hopefully, yeah, I hope that improves your logical understanding of how to do proof by induction. There's a joke that computer scientists are just mathematicians who prove everything by induction. And that's not far off, because as I probably have mentioned before, this is how we think when we're programming. We always think in terms of induction. So it's natural that we try to use it to show the complexity of an algorithm as well. Now, one thing that you won't be doing with substitution method is you won't be substituting in things. I think last year or the year before, I'm not sure, but I would ask students to prove something by using the substitution method. And this is what they did. All right, they would just say, if you have Tn equal to 2 Tn over 2 plus n, that's a recursive formula. They'll start substituting in things. You get some big mess here, and they do some magic, scribble, 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 and then they say, oh, this is n log n. Because they know this is n log n. They just don't know how to prove works. So no, this is not what you're going to be doing. If I ask you to prove something using the substitution method, then you have to use induction. That's how it works. Okay. And with substitution method, there are only two steps. One, you guess the time complexity, and then you use induction. That's it. How do you guess the time complexity? Well, as I mentioned before, you can draw the recursion tree and try to estimate the number of operations. I guess in the previous method, we kind of precisely determine what the number of operation is, right? And I guess, as I mentioned before, even if you can't derive the exact number, you can still try to draw part of the tree and then guess what the complexity is from there, and then use the induction to prove it. You can also use different bounds first and see which one works. Like if you're not sure where the algorithm is, you can try n. If it's too low, then you try n squared. If it's too high, you try n log n. Something like that. You can also guess using heuristic or using experience, as in, oh, this looks like merge sort, or this looks like boundary search, or this looks like near search, or this looks like an n squared algorithm. Right? You can guess that. And the last one is using the Master theorem, which is probably what we all do in real life, to be honest. This is going to be the next lecture. And you're going to be wondering why we're doing recursion tree and substitution method if we have the Master theorem. But we'll get to that in the next lecture. So for our example, we're going to use merge sort again, because we know that's n log n. And this time we're going to use log base 2. I think I'm going to need that later on. But yeah, let's show again that merge sort is n log n. Okay, so how do we do this using induction? Now I'm just going to simplify this bit by saying that when n is equal to 1, we have one operation instead of t to 1. It just makes it simpler, and again, you're not really losing much. You can change the proof by putting 2, 3, 4, whatever you want there, some constant, it'll work the same. Also, I'm not going to be writing log base 2 all the time. I'm just going to be writing log n here, and just assume that's base 2 for this question here. Okay, so if you want to show that merge sort is bigger than log n, then you have to show that Tn is less than or equal to some Cn log n, where C is constant greater than 0. This is just the definition of big O notation from week 1. Okay. Now, with induction, you start with the base case, and we're gonna pick n equal to 1, and immediately you see that we fail because T1 is 1, great, but Cn log n, well, what is log base 2 of 1? It's just 0. So you end up with 0 on the right hand side. So no, this is not true for the base case. So what do you do? Well, you don't have to start from 1. With induction, if you want to, you can start from n equal to 2 or n equal to 3. And you can see that when n is equal to 2 or 3, the statement is correct. So let's use them as a base case. Because you notice if you go to 4, 5, 6, and so on, you don't depend on 1 anymore. Right? T4 depends on T2, T5 depends on T2, T6 depends on T3. So it's okay for T1 to fail. You can't show that this is correct for n equal to 1, but you show that it's correct for n equal to 2, and then everything else builds up from that. This is also a good practice for you, because if you're not sure whether a statement is true or not, then you can try several small n values to see where you can prove it or not. I mean, if you get 4, 5, 6, and you found that you can't get the statement to be correct, like you have to keep on modifying something, then maybe that's not the thing that you want to prove. As in, maybe that's the wrong complexity that you're trying to prove. Okay, so base case, let's use n equal to 3 and n equal to 2. Because these are the two that depends on T1, and well, we just assume that T1 equal to 1, so this is right, and everything else will depend on T2 and T3 now. Right, base case done. Now let's use induction to show what we're trying to show. We have to show that Tn is less than or equal to Cn log n. So induction hypothesis, I'm going to assume that Tk is less than or equal to Ck log k. Right, just putting in k instead of n. Now I have to prove that T2k is less than or equal to 2ck log 2k. Again, I'm just putting 2k inside the equation here. So I get this from the recurrence up here. Right, I get 2tk plus 2k. And then, sorry, I just fixed that. That should be 2ck, not 2k. So that's from the recurrence. And then from the induction hypothesis, we can say that tk is less than or equal to ck log k. So I just put that in there. I end up with this. So can you show that T2k is less than 2ck log 2k? You actually can't. Why can't you? Well, you want to prove that T2k is less than 2ck times log 2k. But what you have there is 2ck log 2k plus 2ck. These are not the same thing. You can't prove the first statement from, you can't prove the first one from the second one. Why? Because it could be the case that T2k is somewhere between 2ck log 2k and 2ck log 2k plus 2ck. Right? Because this is the problem here. Your positive term, 2ck, that's your problem. So we can't do an induction like that. We have to do something else. I'm going to use a different induction hypothesis. So instead of T2K, I'm going to say TK over 2 here. Sorry, instead of TK, I'm going to say TK over 2. So that is the induction hypothesis. I also added K must be greater than 1 here, so we should be fine. Again, let's try this. We have to show that TK is less than or equal to CK log K. Well, plug in the recurrence. So this time we're going from K to K over 2. Use the induction hypothesis. We'll put these in there. And what you see now is that we have the constant here, because you have like K for 2, so that's the whole thing. If you remember your log rules, if you have log A divided by B, that's log A minus log B. So you got CK times log 2 here as a negative, and that should dominate CK. Because log 2, remember we're using log base 2, so log base 2 of 2 is just 1. So that's minus CK plus CK. You got this equal to CK. So we have just shown that TK is less than or equal to CK log K, which is what we want to do, and you're done. Okay, so this is just a standard induction proof. And the only subtlety you have to worry about here is what I wrote here. And that if you want to show the first statement, you can't just use the second statement to do that. And of course, there is a bit of algebra here. I hope you're okay with that. But basically we fix this by using a different induction hypothesis. Okay. Now let's try a different example. Linear search. This is the bit where, this is the version where I divide the array into 3 parts. So the recursive relation is given here. So Tn is 3 times the n over 3. And I'm going to say plus 2, just because we're doing 2 comparison on every level. And we say that T1 and T2 is just equal to 1. As before, it doesn't really matter what you put here. It can be 1, 2, even some constant if you want. But the base case is pretty simple. So when n is equal to 1, well, you see that T1 is just 1, and the right hand side, well, the right hand side is what is Cn with n equal to 1? It's just C times 1, 1, done. So it's true for the base case, n equal to 1. Then what if we try n equal to 2, n equal to 3? Same thing. You can confirm yourself that for these cases the statement is still true. Okay, so base case done. We can actually use n equal to 2 for the base case as well if you prefer. Again, it doesn't really matter as long as you're consistent. Now let's talk about the actual proof. So this is what we want to prove. We want to show that Tn is less than or equal to Cn, so I'm going to assume that Tk is less than or equal to Ck. I'm going to use that as the induction hypothesis. So I have to prove that T3k is less than or equal to 3ck. How do I do that? Let's use the recurrence. Put in the recurrence. So T3k is equal to 3 times Tk plus 2. Just putting that in there. And using the induction hypothesis, we have Tk less than or equal to Ck. So that means the whole thing is less than or equal to 3ck plus 2. Well, or just 3ck plus 2. So can we say that T3k is less than or equal to 3ck? And the answer again is no. What you have shown here is that you have shown that T3k is less than or equal to 3ck plus 2, not less than or equal to 3ck. So same problem that we can encounter earlier with the other example. So what do? We can actually salvage this by proving a stronger bound. So what do I mean? So instead of proving that Tn is less than or equal to Cn, right, I'm going to say that Tn is less than or equal to Cn minus D. I'm going to prove this. Because if I try to prove that, then my assumption would become tk is less than equal to ck minus d for some constant d. And what happens to the proof? Well, same process, but this time instead of just tk, I have ck minus d. So this whole thing becomes 3d, and you have minus 3d plus 2. Now, you want to show that t3k is less than or equal to the right-hand side. Well, less than or equal to 3ck. Can you show this? Yeah, you can. Because if you choose d to be large enough, so for example, if I choose d equal to 2, you'll have here minus 6 plus 2, which is minus 4. So the right-hand side is 3ck minus some number. So in other words, the right-hand side is smaller than 3ck. And we have t3k is less than or equal to that right-hand side. You know, t3k is less than something, and that something is less than 3ck. So t3k is less than or equal to 3ck. And because if Tn is less than or equal to Cn minus d, is that still big O of n? Yeah, because all matters is the C and the n. The constant here doesn't really matter, remember? Because if you're doing complexity, the constants don't matter. So there you have it. We have proven that Tn is big O of n. So remember how I mentioned that this lecture is more about teaching you how to be more careful with induction. So this is the main point here, right? If you want to show that Tn is less than or equal to Cn, you can't just show that Tn is less than or equal to Cn plus some constant, plus something which is bigger. Because what happens is Tn might be somewhere between Cn and Cn plus 1 or plus whatever. And there are two ways. We try to fix that using two different ways. One is that we change the assumption, we change the induction hypothesis. In the example that you saw, I went from 2k to k to k over 2. Or you can also use a weaker bound. You can try to prove a weaker bound. That's the second example, right? So these two techniques, hopefully you remember how to use them. We can do one more example. So this one is similar to the last example in the previous lecture. So we have 3Tn over 4. Again, I'm going to guess the complexity to be n squared. So we have to show that Tn is bigger of n squared. Now, is the base case alright? Yep. For n equal to 1, the left hand side is just 1, the right hand side is n squared, so it's just 1 squared, and that was for 2 and 3 as well, for n equal to 2 and n equal to 3. All fine here. You can go further to, I went with 4, 8, and 16 here, like multiples of 4, so I have a feel on whether this is correct or not. Like I said, like sometimes I'm not sure if what I'm trying to prove is actually correct, if it's actually possible. So I put in different values of n just to get a feel. This is not the proof. I know there are students who like to prove something is correct by using different values of n and say, hey, this is correct. No, that's not how it works. This is just me getting a feel of whether or not the statement is true. And here I can argue that the right hand side is always 16 squared. It's always like a square of the number times some constant. And I can see here that the right hand side here of the second term of the left hand side is always that square as well. Whereas the left hand side, the left side is something smaller. So I'm kind of certain that this is n squared. Well, this is big O n squared. Let's get the proof. So this time I'm using the hypothesis that t k over 4 is less than or equal to c k over 4. So this is similar to the first example. So again, use the recurrence equation, plug that in, replace this with k, and then use the induction hypothesis. So tk over 4 is less than or equal to ck squared divided by 16. Right, I'm just expanding that. And we come up with this same equation here. We have a constant in front of k squared. So this one's actually easier than the previous two. Well, assuming you already know how to use the correct induction hypothesis. All right. So that's pretty much all we're doing for this lecture. If you want to refer to the textbook, it's on chapter 4, pages 84 and 86, up to 86. So maybe you can use that to supplement this lecture. I'm pretty much basing what I'm doing here from the textbook anyway, so you should be reading the same thing. So as I said, this is just like another proof by induction, like another way that you can use induction. And the result is not as precise as the recursion tree method, because again, with the recursion tree, you're counting almost exactly how many operations that you're doing on the tree. Whereas now, because we're just using induction, it's more used for upper bound or lower bounds, like big O notation or omega notation, not really type bound. Now, what do you need to know about this technique? Well, you can expect to see a recursion tree method question in the exam or test. And then the question normally goes, use the recursion tree to like work out a bound and then use induction to prove it. Right, so it's almost like one package when you see this kind of questions. And hopefully that's what you do as well if you encounter this in real life, and if you have to work out some bounds, complexity bounds, you know how to use induction for it, at least as a good start. Okay, one more lecture about master method, and then that's it for this topic. I'll see you then.